US Physics Olympiad year 2015 USAPHO Final Exam. This exam consists of 6 problems, Part A 4 problems and Part B 2 problems. For each part they were given 60 minutes. Solutions for all problems you can find below this video in the reference of the description. If you want to check many other problems from US Olympiad or whatever, you can subscribe to this channel. Problem A. Consider a particle of mass m that elastically bounces off of an infinitely hard horizontal surface under the influence of gravity. The total mechanical energy of the particle is E, and the acceleration of free fall is g. Treat the particle as a point mass and assume the motion is non-relativistic. Question A. An estimate for the regime where quantum effects become important can be found by simply considering when the de Broglie wavelength of the particle is on the same order as the height of a bounce. Assuming that the de Broglie wavelength is defined by the maximum momentum of the bouncing particle, determine the value of the energy EQ where quantum effects become important. Write the answer in terms of sum of all, or G, M, and the Planck constant H. Solution. From definition of de Broglie wavelength, we can write that momentum P equal h over lambda, where h is Planck's constant and lambda is de Broglie wavelength. Now, because we consider that lambda equal height, we can write these relations. Total energy of bouncing equal mgh, which is equal to p square over 2m. Now we can use p as this expression and lambda equal h. So we have this relation, and from here we can find what is height h. For h we have this expression, and after all energy equal this formula. That's root 3 from mg square h square over 2. This is the answer for question A. Part B. A second approach allows us to develop an estimate for the actual allowed energy levels of a bouncing particle. Assuming that the particle rises to a height h, we can write this equation, where p is the momentum as a function of height x above the ground, n is non-negative integer, and the h is Planck's constant. First, determine the allowed energies En as a function of integer n, and sum all of Gm and Planck's constant h. 2. Numerically determine the minimum energy of a bouncing neutron. The mass of a neutron is this one in kilograms or mega electron volts per c square. You may express your answer in either joules or electron volts. 3. Determine the bounce height of one of these minimum energy neutrons. Solution. First of all, we can write that energy equal potential energy mgx plus kinetic energy momentum square over 2m, and we can express this p P from this formula and use presented formula. Momentum equal this formula, and now we can use this to this integral, and we have to take this integral. That will be, and for this integral we have this answer, and from here we can find the energy levels as a function of n. So energy levels will be equal to this formula as a function of number n. And now we can estimate what are energy levels for neutron. We can estimate what is the minimum energy level for neutron for n equals 0. That will be approximately 1.1 multiplied by 10 power negative 12 electron volts. That's the answer for second question. And finally, for third question, we have answer height h equal 0 minimum energy level over mg, which is about 10 microns. Part C. Let E0 be the minimum energy of the bouncing neutron and F be the frequency of the bounce. Determine an order of magnitude estimate for the ratio E over F, if only needs to be accurate to within an order of magnitude or so, but you do need to show work. Solution. Height equal 1/2 gt square. From here we can find what is time to fall down for neutron, and the frequency equal just 1 over t, which is about 175 Hz for our calculated height. And finally, when we estimate what is energy over frequency, that will be this one over this one, which is 6.3 multiplied by 10 power negative 16 electron volts multiplied by seconds, which is close to Planck constant. Planck constant has a coefficient 6.6 here with the same power. US Physics Olympiad year 2015 USAPHO final round. Problem A2. Consider the circuit shown below. IS is a constant current source, meaning that no matter what device is connected between points A and B, the current provided by the constant current source is the same. Question A. Connect an ideal voltmeter between A and B. Determine the voltage reading in terms of any or all of R and the IS. Question B. Connect instead an ideal ammeter between A and B. Determine the current in terms of any or all of R and IS. Question C. It turns out that it is possible to replace the above circuit with a new circuit as follows. From the point of view of any passive resistance that is connected between A and B, the circuits are identical. You don't need to prove this statement, but you do need to find IT and RT in terms of any or all of R and IS. Solution for question A. Using voltmeter between points A and B equivalent to using infinite resistance here. So we can replace this picture by equivalent picture. And due to symmetry, we have the same current IS over 2 through both branches. And now we can count what is the potential difference between A and B. Suppose that the potential of bottom part is 0. It means that the potential in point A will be IS multiplied by R, and the potential in point B will be 2ISR, and the potential difference will be UB minus UA, which is IS multiplied by R. That's the answer for question A. Solution for question B. Using ammeter means that we are creating shortcut between A and B, and we can change this picture for equivalent. Due to symmetry, we have current I1 is going through resistor 4A in the up left corner and in the lower right corner, and the current I2 is going through resistor 2R in the upper right corner and the lower left corner. And suppose that current I3 is going to the left. Now we can write three equations to find what are all these currents. Current I1 plus I2 equal IS. That's the first equation. Current I2, which is going here, it is split to I3 and I1, which is the second equation. And the third equation is potential difference between this point and this point. We can get from this way, which is 4RI1, this one, or we can go by this way, which is 6RI3 plus 2RI2, which is this way. So we have three equations and three unknown currents, and we can solve this system. Now we can exclude I2 and put it in first and third equations. We have these two equations, and from here we can find that I1 equal 4I3, and we put it in this equation, and finally get that I3 equal IS over 9. That's answer for question B. Part C. If we don't need to prove this statement, we can just use results from A and B parts. Suppose that here we put a shortcut. It means that the current here will be IS over 9, and because it's full current, this source must have this current IS over 9. And now suppose that here we put infinite resistance. In that case, voltage will be IS multiplied by R, which must be equal IT multiplied by RT. And from here we can find that RT equal 9 times R. So that's the answer for question C. US Physics Olympiad, year 2015, USA, PHO. Problem A3. Solution for this problem you can find below this video in the reference of the description. A large block of mass MB is located on a horizontal frictionless surface. A second block of mass MT is located on top of the first block. The coefficient of friction, both static and kinetic, between the two blocks is given by μ. All surfaces are horizontal. All motion is effectively one-dimensional. A spring with the spring constant K is connected to the top block only. The spring obeys Hooke's law equally in both extension and compression. Assume that the top block never falls off of the bottom block. You may assume that the bottom block is very, very long. The top block is moved a distance a away from the equilibrium position and then released from rest. Question A. Depending on the value of A, the motion can be delivered in two types: motion that experiences no frictional energy losses and motion that does. Find the value AC that divides the two motion types. Write your answer in terms of any or all of mu, the acceleration of gravity g, the masses mt and the mb, and the spring constant k. Question B. Consider now the scenario when amplitude A much greater than AC, A critical. In this scenario, the amplitude of the oscillation of the top block as measured against the original equilibrium position will change with time. Determine the magnitude of the change in amplitude delta A after one complete oscillation as a function of any or all of A, mu, g, and the angular frequency of oscillation of the top block omega t. Question C. Assume still that amplitude much greater than AC. What is the maximum speed of the bottom block during the first complete oscillation cycle of the upper block? Solution for the first question. Maximum possible force exerted by spring on both blocks is Ka equal total mass of both blocks multiplied by their common acceleration when they stick together. It means that acceleration equal Ka over total mass. But this acceleration could provide for the bottom block only force of friction, which is maximum possible mu mass of the top block multiplied by g. So it means that critical amplitude we can find from this equation, where on the left we have maximum possible force of friction, and on the right we have mass of the bottom block multiplied by this acceleration provided by critical amplitude AC. From here we can find what is this AC. That will be this expression. And this is the answer for question A. Solution for question B. On this diagram it's easy to show total solution. If we have oscillation without friction, that will oscillate on a black line from rightmost position to the leftmost position. But if we have a force of friction, which is acting most of the time on the top block, we have position of equilibrium shifted by distance dx, which can be found from this equation. Dx equal force of friction by constant k. And this position shifted to the right from original equilibrium position. It means that when this block moving to the left, it will stop on a distance 2 dx to the right from original leftmost position. Now when it will stop, it starts to oscillate to the right, but now this position of equilibrium is shifted by dx to the left from original position of equilibrium. It means that total amplitude, when it's moving to the right, it will be shorted by 3dx, and it will stop by 3dx less from this position of equilibrium. But because it's shifted by dx, total stop point will shift by 4dx from the rightmost position. So it means that total amplitude will change by 4dx. And solution for this question is 4dx, which is 4 mil mt g over k. That's the answer for question B. Solution for question C. When top block moving to the left, it exerting force of friction to the bottom block during half of period of this oscillation for the top block, and period equal 2 pi multiplied by square root from mt over k, and the total time this block will accelerate bottom block is t over 2, which is this one. During this time, the top block will act with a force mu mtg on the bottom block, which accelerated with the amount of mu mtg over mu b. And now to find what is the total maximum speed in the end of this process, that will be acceleration multiplied by time, which is this expression. That's the answer for question C. US Physics Olympiad, year 2015, USAPHO. Final exam. Problem A4. A heat engine consists of a movable piston in a vertical cylinder. The piston is held in place by a removable weight placed on top of the piston. But piston stops prevent the piston from sinking below a certain point. The mass of the piston is M equal 40 kg. The cross-sectional area of the piston is 100 square centimeters, and the weight placed on the piston has a mass of 120 kg. Assume that the piston around the cylinder and the piston is a vacuum, so you don't need to worry about external atmospheric pressure. At point A, the cylinder volume V0 is completely filled with liquid water at a temperature 320 kelvins and the pressure P minimum. That would be just sufficient to lift the piston alone, except the piston has the additional weight placed on top. Heat energy is added to the water by placing the entire cylinder in a hot bath. At point B, the piston and the weight begins to rise. At point C, the volume of the cylinder reaches V maximum and the temperature reaches 400 kelvins. The heat source is removed. The piston stops rising and is locked in place. Heat energy is now removed from the water by placing the entire cylinder in a cold bath. At point D, the pressure in the cylinder returns to P minimum. The added weight is removed. The piston is unlocked and begins to move down. The cylinder volume returns to V0. The cylinder is removed from the cold bath. The weight is placed back on top of the piston and the cycle repeats. Because the liquid water can change to gas, there are several important events that take place. At point W, the liquid begins changing to gas. At point X, all of the liquid has changed to gas. This may not occur the same as at point C described above. At point Y, the gas begins to change back into liquid. At point Z, all of the gas has changed back into liquid. When in the liquid state, you need to know that for water kept at a constant volume, a change in temperature delta T is related to change in pressure delta P, according to delta P approximately equal 10 power 6 Pascal per Kelvin multiplied by delta T. When in the gas state, you should assume that water behaves like an ideal gas. Of relevance to this question is the pressure-temperature phase plot for water, showing the regions where water exists in liquid form or gaseous form. The curve shows the coexistence condition, where water can exist simultaneously as gas or liquid. The following graphs should be drawn on the answer sheet provided. Question A. Sketch a PT diagram for this cycle on the answer sheet. The coexistence curve for the liquid-gas state is shown. Clearly and accurately label the locations of point B through D and W through Z on this cycle. Question B. Sketch a PV diagram for this cycle on the answer sheet. You should estimate a reasonable value for V maximum. Note the scale is logarithmic. Clearly and accurately label the locations of points B through D on this cycle. Provide reasonable approximate locations for points W through Z on this cycle. Here are solution diagrams for this problem, and let's explain them. First, we start by computing pressures. The minimum pressure is when only the piston is to be lifted. So we have P minimum equal weight of piston mg over cross-sectional area A, which is 40 kilopascals. The maximum pressure is when lifting the piston plus extra weight, and extra weight is 120, so total is 160, and P maximum will be 160 kilopascals. And point A is clearly at P minimum and T0. For liquid water, a small temperature increase results in a large pressure increase. So point B is effectively at the same temperature as the point A. Process A to B is therefore essentially isothermal, and it is also constant volume process. After that, the pressure is sufficient to lift the piston plus extra weight, so the volume expands at a constant pressure for the process B to C. However, liquid cannot change to gas until we reach the coexistence curve. This defines the location of point W on the PT graph, where are stuck on the coexistence curve until all the liquid has changed into gas. So X and C are also at the same point. It is expected that the examinee will know that liquid water will only expand slightly when heated over the temperature range. So point W must be very close to V equal V0 on the PV diagram. Upon reaching C, the piston is locked in place, constant volume, and the cylinder is allowed to cool. To figure out what happened, consider the ideal gas law. PV equal nRT. For a constant volume process, the temperature of the gas is proportional to the pressure, implying that it would follow a straight line toward the origin of PT. But this forces us back into the liquid region of the graph, so instead we must follow the coexistence curve down, immediately changing gas back into liquid. A such Y is at the same location as C and X. The next process, C to D, is a constant volume, but not isothermal. On PT graph we follow coexistence to the minimum pressure, at which time the piston is freed and allowed to lower at constant pressure. Since Z is the point where all of the gas has changed to liquid, it must be on the coexistence curve, but on PV diagram it is just to the right of point A. It is expected that the examinee will know that the volume of the gaseous state is on the order of 2000 times the volume of the liquid state. Points A and B must be at the correct location in both figures. Points C, D, W, X, Y, and Z must be at the correct location in the RT diagram. Points C and D must be at the correct pressure, but in the V range 1000 to 5000 for the PV diagram for partial credit. Points X and Y must coincide with the C on the PV diagram. Points W and Z must be at the correct pressure, but can be located in the V range 1 to 2 for full credit, but 2 to 5 for partial credit. US Physics Olympiad, year 2015, USAPHO, final exam. Problem B1. This problem is divided into two parts. It is possible to solve these two parts independently, but they are not equally weighted. Part A. An ideal rocket, when empty of fuel, has a mass mr and will carry a mass of fuel mf. The fuel burns and is ejected with an exhaust speed of Ve relative to the rocket. The fuel burns at a constant mass rate for a total time Tb. Ignore gravity. Assume the rocket is far from any other body. Question 1. Determine an equation for the acceleration of the rocket as a function of time t in terms of any or all of t, mf, mr, ve, tb, and any relevant fundamental constants. Question 2. Assuming that the rocket starts from rest, determine the final speed of the rocket in terms of any or all of mf, mr, ve, tb, and any relevant fundamental constants. Solution for question 1. Because momentum is constant, we can write that mv is a constant So we can take a first derivative from this expression, and we have this equation. But mass equal this expression, and dm over dt equal this expression. So now we can write what is the acceleration. So acceleration equal dv over dt, or this expression, which is answer for question 1. For question 2, we can rewrite this formula in form of this equation. Now we can take a full integral and find that speed v equal this expression when we use all fuel. That's the answer for question 2. Part B. The ship starts out in a circular orbit around the Sun, very near the Earth, and has a goal of moving to a circular orbit around the Sun that is very close to Mars. It will make this transfer in an elliptical orbit as shown in bold in the diagram below. This is accomplished with an initial velocity boost near the Earth, delta v1, and then a second velocity boost near Mars, delta v2. Assume that both of these boosts are from instantaneous impulses, and ignore mass changes in the rocket as well as gravitational attraction to Earth, to either Earth or Mars. Don't ignore the Sun. Assume that the Earth and Mars are both in circular orbits around the Sun of radii Re and Rm equal Re over alpha respectively. The orbital speeds are Ve and Vm respectively. First question. Derive an expression for the velocity boost delta v1 to change the orbit from circular to elliptical. Express your answer in terms of Ve and alpha. Second question. Derive an expression for the velocity boost delta v2 to change the orbit from elliptical to circular. Express your answer in terms of Ve and alpha. Third question. What is the angular separation between Earth and Mars as measured from the Sun at the time of launch, so that the rocket will start from Earth and arrive at Mars when it reaches the orbit of Mars? Express your answer in terms of alpha. Solution for question 1. First of all, we can find what is the speed around Sun. We use this formula for centripetal force, which is equal to force of gravity. From here we can find that speed equals square root from g mass of Sun over radius Re, and for the same reason we have speed Mars is this one, or using coefficient alpha we can express it through speed Earth. These expressions we will use later. So this problem we can find directly using energy conservation and momentum conservation, but this is the long way. I can show you just formulas for that, but you could solve them yourself. I will show you a shortcut. First equation is angular momentum conservation. If speed v1, that's the speed of this rocket just in the shortest position on a distance Re, we multiply it by a radius of orbit of Earth, and that's equal to v2, which is speed in the point of Mars orbit, and multiplied by distance from Mars to Sun. That's angular momentum conservation. And also we have energy conservation. For energy conservation, we have this expression that full energy of a rocket, which is kinetic energy plus potential energy in closest point, equal to kinetic energy and potential energy in furthest point of this ellipsis. And if we have these two equations, and we have two unknown velocities v1 and v2, we can find them through expression of square root from gm, and later use to find what is delta v1 and delta v2. But this is kind of a long story. I can show you a shortcut. If you remember third Kepler law, from this law we can conclude that period of rotation depends only from size of big axis of ellipsis. In our case that's Re plus Rm. But not only period depends from this size, also full energy depends only on this size, Re plus Rm. And this is the shortcut. So to find what is the full energy, we can use this expression. So if you can see, the total energy on the elliptical orbit equal to this expression. That is from one hand, and from other hand that's equal to kinetic energy in the closest point plus potential energy in the closest point. That will be this expression, and from this expression we can find immediately what is V1. So from this equation we can find that V1 equal this expression, or using V1 and alpha we can write delta V1 equal this expression, which is answer for question 1. For question 2 we have similar solution. Due to symmetry we can write that V2 equal this expression. We just exchange Re and Rm, and finally that's equal to this expression, and finally we will get for delta V2 we have this solution, which is answer for question 2. Solution for question 3. Here we can use the third Kepler law to solve this problem. From third Kepler law we have time to travel for this rocket divided by period of Mars. That's equal this expression or this expression. For this time Mars travel by angle 2 pi multiplied by this relation, which is this one, and the rocket travel for angle pi. It means that the total angle between Earth and Mars, as seen from Sun in time of launch, equal this expression, which is the answer for question 3. US Physics Olympiad, year 2015, USA PHO, final exam. Problem B2. The nature of magnetic dipoles. Part A. The Gilbert dipole consists of a pair of magnetic monopoles, each with a magnitude Qm, but opposite magnetic charges, separated by a distance d, where d is small. In this case, assume that negative Qm is located at z equals 0, and positive Qm is located at z equals d. Assume that magnetic monopoles behave like electric monopoles according to a Coulomb-like force F equal mu0 over 4 pi multiplied by qm1 qm2 over r square, and the magnetic field obeys B equal F over qm. First question: what are the dimensions of the quantity qm? Second question: write an exact expression for the magnetic field strength Bz along the z-axis as a function of z for z greater than d. Write your answer in terms of qm, d, z, and any necessary fundamental constants. Third question: evaluate this expression in the limit as d going to 0, assuming that the product qmd is pm is kept constant, keeping only the lowest non-zero term. Write your answer in terms of pm, z, and any necessary fundamental constants. Solution for question 1. What are the dimensions of the quantity qm? From a second equation we have dimension for qm equal dimension for force divided by dimension for magnetic field. But force equal current multiplied by length multiplied by magnetic field. If we put this expression to this expression, magnetic field is cancelled, and we have finally dimension for qm equal ampere multiplied by meter. That's the answer for the first question. Solution for question 2. Here we can use definition in the first and the second formula. So we have, by definition, magnetic field has this expression, and finally we can get this formula. Solution for question 3. Now when we have limit d going to 0, we can estimate this part of expression, and we have this estimation. For small d, that's approximately equal this expression, and finally 2d over z. And now we can put this to this formula and get this final answer for magnetic field, where pm is qm multiplied by d. So that's the answer for question 3. Part B. An ampere dipole is a magnetic dipole produced by a current loop I around a circle of a radius r, where r is small. Assume that the z-axis is the axis of rotational symmetry for the circular loop, and the loop lies in the xy plane at z equal 0. First question: write an exact expression for the magnetic field strength Bz along the z-axis as a function of z for z greater than 0. Write your answer in terms of I, R, Z, and any necessary fundamental constants. Second question: let K, I, R power gamma have dimensions equal to that of the quantity Pm defined above in part A3, where K and gamma are dimensionless constants. Determine the value of gamma. Question 3. Evaluate the expression in part B1 in the limit as r going to 0, assuming that the product Ki r power gamma equal to Pm prime is kept constant, keeping only the lowest non-zero term. Write your answer in terms of k, pm prime, z, and any necessary fundamental constants. Question 4. Assuming that the two approaches are equivalent, pm equal pm prime, determine the constant k in part B2. Answer for question 1. Write an exact expression for the magnetic field strength Bz along the x-axis of a function of z for z greater than 0. We can use here Biot-Savart law and calculate this Bz. That will be mu0I over 4 pi multiplied by circular integral dl cross product with the s divided by s cube, where s is a vector which is going from a point on a circle to point in axis z, and finally we have this expression multiplied by sine theta, and theta, that's the angle between axis z and the vector s. And finally we have this answer for question 1. Solution. We know from part A3 that pm has dimension ampere multiplied by meter square. It means that gamma equal 2. That's the answer for question 2. Question 3. Evaluate the expression in part B in the limit as r going to 0, assuming that the product ki r gamma equal p m prime is kept constant, keeping only the lowest non-zero term. Solution. We have a solution for Bz equal this one, and if we know that r square is constant and the denominator going to z cube here because r going to 0, we can rewrite this expression in form of this one. This is the answer for question 3. Question 4. Assuming that the two approaches are equivalent, pm equal pm prime, determine the constant k in part B2. Solution. Because in part A magnetic field was this expression, and here magnetic field is this expression, and pm equivalent to pm prime, we have k equal pi. That's the answer for question 4. Part C. Now we try to compare the two approaches if we model a physical magnet as being composed of densely packed microscopic dipoles. A cylinder of this uniform magnetic material has a radius r and a length L. It is composed of n magnetic dipoles that could be either all Ampere type or all Gilbert type. N is a very large number. The axis of rotation of the cylinder and all of the dipoles are all aligned with the z-axis and all point in the same direction as defined above, so that the magnetic field outside the cylinder is the same in either dipole case, as you previously determined. Below is a picture of the two dipole models. They are cubes of side d much less than r and d much less than l, with the volume Vm equal d cube. First question. Assume that r much greater than l and only Gilbert-type dipoles determine the magnitude and direction of B at the center of the cylinder in terms of any or all of Pm, R, L, Vm, and any necessary fundamental constants. Solution. The monopoles that make up the dipoles cancel out except on the flat surfaces. Then the cylinder acts like a parallel plate capacitor. If the size of a dipole is d, then the surface density of monopole charge is sigma m equal qm over d square. Using the analogy with the parallel plate capacitors, the magnitude of B is mu0 sigma m, which is equal mu0 pm over d cube, and the direction is to the left. That was the answer for question 1. Question 2. Assume that R much less than L and only ampere-type dipoles determine the magnitude and direction of B at the center of the cylinder in terms of any or all of Pm, R, L, Vm, and any necessary fundamental constants. Solution. The currents that make up the dipoles all cancel out except on the cylindrical surfaces. Then the cylinder acts like a solenoid with B equal mu0 I over d, where I over d is the surface current density. The magnitude of magnetic field B is this one, and the direction is to the right. That was answer for question 2.